Hi everyone. Today we will be presenting our project design, the Articulate.
Hello, my name is Scott Bell. I have served 18 years in the Air Force, 12 on active duty as a bioenvironmental engineering technician, and 6 as a communicator with the Florida Air National Guard. I am currently pursuing a Bachelor's of Science degree in Electrical Engineering at UCF with a minor in Robotic and Intelligent Systems. For our senior design project, I was responsible for the mechanical design, servo control, and assisted with circuit design of the system. I have recently accepted a position at Aeronix as a hardware FPGA engineer.
Hello, my name is Ken Chu. I'm currently pursuing a Bachelor of Science in Electrical Engineering at UCF. For our project, I designed the circuit PCB and responsible for all the electrical testing as well as assisting in mounting of the hardware. I have accepted and started working for Lockheed Martin as a system integration test engineer at Kennedy Space Center. I'm currently on the Artemis Orion program supporting the launch abort system on the Orion crew module.
Hi, I'm Michael Tal. I'm currently pursuing a Bachelor's of Science in Electrical Engineering. For our project, I focused on the layout of the components for our design, as well as testing some of the electrical components, and I also worked on the administrative part, such as the financing and managing the group assignments. For my future plans, after graduating with my Bachelor's of Science in Electrical Engineering degree, I plan on going to grad school at UCF for a Master's in Business Administration.
Hi, my name is Benjamin Sims. I enrolled at UCF after I graduated high school in the computer engineering program. For this project, I did the research on the computer vision and implemented it, and I wrote most of the Python code. After graduating, I plan on being a software engineer, and I hope you enjoy the project.
Motivation. Our motivation for wanting to design the Articulate is because we feel it would be beneficial for workbenches around the world. Imagine this, being able to work on a project without having to deal with shadowing. With the Articulate, the user has the choice to make a hand gesture and it will control the light to move to the dedicated position, giving the maximum light possible with minimum shadowing. This will allow users to finish and produce projects at a faster rate. Goals and objectives. Articulate offers many great benefits. These benefits include, but are not limited to, hands-free light for workbenches, light direction movement through hand gestures and view of a camera, a hand-following algorithm, and a move to hand algorithm for articulating arm with light attached, and it allows for less shadowing when working on a project. Market requirements. For our design, we had some general specifications that we wanted to make sure the market received. These are pitch slash yaw and angle slash degrees of freedom, which basically allows a plus minus 9 degree of movement in basically the left, right, up, and down directions. Robot vision, which will be using a camera to identify hand gestures to control the actuation. The stand will allow our design to be mounted vertically or horizontally. Environmental robustness, be able to handle temperature and humidity variation. We were able to have the design work between 20 degrees to 100-degree temperature range, and also make it waterproof and dustproof as best as possible. For the response time, we wanted to make sure that the software to hardware interface was less than 3 seconds each. We also wanted to set a manual reset serialize. That way the device will be able to manually stop and reset the system. Key specifications. There were four main key specifications that we as a group decided to focus on. These four were accuracy, durability, actuation time, and computation time. For accuracy, we wanted it to be less than or equal to 1 centimeter of where the user designated the light to go. For durability, we wanted the user to get at least 1,000 or more uses out of it. For actuation time, we wanted it to be between 3 to 5 seconds. This is the time that it takes for the task to be completed for movement. And lastly, computation time. We wanted this to be less than or equal to 2 seconds. We wanted the system to read the gesture within 2 seconds or less. Next, we will be looking at our hardware components. Hardware block diagram. In the diagram below, you will see how the components were connected to one another. Starting off on the far left, you have our power supply. This was a 12-volt wall plug-in power supply that would be plugged into a 120-volt AC wall outlet. After, the power supply was split into two. One would flow to the light, and then the other would flow to the voltage regulator, which controlled the other components. So the 12-volt power would then be dropped down to 5 volts at the voltage regulator to power our microcontroller. Our microcontroller then sent messages to the Jetson Nano, which then received the message to the camera. The microcontroller also powered our servo motors, which control the pulleys, which helps activate the arm articulation by controlling the direction in which the user wants the light to go. Microcontroller. There are three main microcontrollers that we were looking at for our design. These are the Atmega 328P, the MSP 430 G2553, and the STM 32G031 F8P6. We chose the Atmega 328P microcontroller because we felt it had the best specs for our project and it was the most convenient for servo control. Some of these specs of the Atmega include, but are not limited to, having an input voltage of 1.8 to 5.5 volt DC, an operating voltage of 1.8 to 5.5 volt DC, having 27 digital I input-output pins, and having 10 PWM channels.
Since our project implements computer vision in an embedded environment, a powerful enough embedded computer must be selected. We took a look at two options, the NVIDIA Jetson Nano and the Raspberry Pi 4. The Jetson Nano made by NVIDIA has 4 GB of RAM and was designed for embedded deep learning, such as computer vision. It can do computations that are necessary for AI tasks in parallel, which makes it very powerful in an embedded environment. It runs a modified version of Ubuntu Linux called Jetpack. The Raspberry Pi 4 comes in either 4 or 8 GB of RAM. It has capabilities to run computer vision software such as OpenCV and MediaPipe, which is a library that maps the hands. Although it can contain more RAM than the Jetson Nano, it doesn't have any architecture specifically for deep learning. It runs a modified version of Debian Linux called Raspberry Pi OS. We chose the Jetson Nano Developer Kit as it seemed to be a better fit for our project. The Jetson Nano is marketed for uses such as ours. It would also allow a more in-depth experience in machine learning due to its architecture. This architecture is its 128-core Maxwell GPU and its ARM A57 CPU. It has CSI camera connections and a 40-pin GPIO header for communication with other devices. It runs at a 5-volt 2-amp input with 3.3-volt output pins.
Motor selection. In the table below are the servo motors considered for our project. We decided to go with the D956WP because it can operate at the same voltage as the Jetson Nano. This means we do not have to add additional regulation to the circuit. It also has a rotation of 180 degrees. Furthermore, it also has a high maximum torque to accommodate the length of the arm and is also waterproof. Camera. There are 5 different cameras that we were looking at. These are the Raspberry Pi Camera Module 2, the Raspberry Pi High Quality Camera, the ArduCam IMX219 Visible Light Fixed Focus Camera, the ArduCam IX219 AF Programmable Autofocus Camera, and the ArduCam IMX219 Low Distortion M12 Mount Camera. After researching each camera and testing them, we decided to go with the Raspberry Pi Camera Module 2. For its image sensor, it uses an IMX219, has a max resolution of 8 megapixels, has a horizontal FOV, which is the degrees, of 62.2, has a full resolution frame rate, which is non-applicable, a 60 FPS, and at a decent price of $25. Socket specifications using a LED bulb. There were 4 different types of socket sizes that we looked at. These are E12, E19, E26, and E39. For our design, we decided to use a normal household socket, which is the E26. The E26 offers 60 watts of power, 250 volts, luminosity of 800 lumens, is 26 millimeters, and weighs 0.564 ounces. Voltage regulator. There are 2 types of voltage regulators: linear and switching. Linear voltage regulators have low output ripple voltage, fast response times, and low electromagnetic interference, and less noise. However, they're not that efficient. It requires large space, and voltage above the input cannot be increased. For switching regulators, they have a more complex design, which allows for higher power efficiency. Furthermore, it's able to provide output which can be greater or less than the input voltage. However, switching voltage regulators give higher output ripple voltage, it has a slower transient recovery time, is very noisy, and is very expensive.
For our project, we decided to go with a flexible robotic arm, also known as a continuum robotic arm. The arm is controlled by 2 servo motors connected to pulleys that enables movement in the X and Y coordinate system. All of the segments are used as wire guides, which are fastened to the camera mount. Every component was 3D printed, which allowed us to rapidly prototype and test the system. The mechanical design of the Articulite can be broken down into 5 major components: the segments and wire guides, the camera mount, the servo mount and stands, the pulley design, and the case or housing. Camera mounts. 2 versions of the camera mount were designed. One for the ONN USB webcam. This has a slot in the top that allows the camera to be mounted with a bolt. The second is designed to accommodate the legs of a Raspberry Pi camera stand. A segment model was used as the template with 2 legs extended from the top and altered for each camera. The center hole was also widened to accommodate the light socket. The center hole was then widened. The servo mount and stands. The servo mounts were designed as an L bracket with bolt holes that lined up with the servo mounting holes. The original design was not strong enough to account for the amount of torque placed on them by the actuation of the arm, so we made the mounts nearly 3 times thicker. The stand was made from L brackets for corner joints and sheet copper. The bracket provides stability for the servos during actuation, not allowing them to flex, and the copper extends behind the motor to both give it more rigidity and act as a heat sink. Pulley design and cable selection. The pulley is designed to allow the motor center gear to connect to an inset actuation control mount, along with the mounting holes for the bolts to secure it in place. The inset mount distributes the force across the pulley instead of to the mounting bolts. A set screw was added to fix the wire to the pulley. Deep sea fishing line was selected for the guide wire because it is a coated steel wire that is very strong and very flexible. The coating is ideal for increasing the longevity of the wire guides. Case or housing. The case was originally built out of plexiglass with 3D printed corner connectors. The connectors allowed us to assemble the case without using hardware such as bolts and screws. Upon testing, we noticed that the plexiglass would flex when the arm was moving. This was skewing our testing results since the amount of flexing was not consistent. This would also likely cause the case to break over time. The case was then redesigned to be sturdier using wood. This added the rigidity and strength needed to prevent excess movement from the servos. A double hinge design was implemented to allow us to open the case further, giving us easier access to all of the components.
Electrical design. We're going to discuss the PCB design for our project. This is an overall view of our circuit. Basically, 120 volts goes into our circuit board. Voltage gets stepped down to about 12 volts. It goes into two single-stage bridge rectifier. Then it splits into two voltage regulator. On one side, it powers higher current device like the Jetson Nano and servo motors, while the other one will power the Atmega microcontroller with a lower current. The microcontroller circuit is designed where the lower current will power pins 7 and 20 and share the common ground for the whole circuit. We added a 16 MHz crystal oscillator to the microcontroller so that it would produce a clean clock signal to the board and send an accurate pulse width modulation signal from the microcontroller to the motors. This is an overall view of our power supply voltage regulator. 120 volts AC is going into the step-down transformer, then it outputs 12 volts AC. From there, it's going to go to a single-stage bridge rectifier which converts the AC signal into a DC signal. Since this DC signal is not a pure DC signal and it still has ripples, we added capacitors to smooth out the ripples. Then from there it goes to a voltage regulator that reduces it to 5 volts where it then powers our 5 volt devices. Our basic functionality of our circuit board is to utilize 120 volts AC for our light while reducing the voltage to power our electronic devices. Also to convert the AC signal into a DC signal while controlling the amperage by providing a higher amperage to devices that needs a higher amperage while reducing the amperage to devices that might be sensitive to overcurrent. After the power exits the transformer, power then gets split into two. One half exits the bridge rectifier and goes into a voltage regulator which uses a PNP transistor which outputs a higher amperage to power the Jetson Nano and servo motors, while the other voltage regulator carries a lower amperage powering our microcontroller.
PCB design. The PCB was designed using EasyEDA software and printed at JLC PCB. PCB design continued. Once we received the PCB from JLC PCB, we tested all of the traces using a multimeter and then mounted all of the components and tested all of the traces again to verify connectivity throughout the circuit.
Now, let's get into the software design of the project. To implement gesture detection on our project, we modified and extended an existing project made by NVIDIA to fit our needs of the project. This project was TRT Pose Hand. It uses TensorRT with Python which natively integrates into the Jetson Nano hardware. This project supplies us with a ResNet 18 convolutional neural network that was retrained specifically for returning key points on hands. Using the output of the ResNet model, we can train a support vector machine through sklearnlater to do the gesture detection software. When we initially researched image detection, we thought we would train our own convolutional neural network model. However, after doing more research and discovering TRT pose hand, we chose to just use the ResNet 18 hand model and training an SVM on top of it. We did this for two reasons. Training our own convolutional neural network model would take a lot more time than to implement one that already exists and using an SVM that can be trained on just a few lines of code. Additionally, since we plan on using the results of the gesture detection for directional instructions for servo motors to move, the ResNet 18 hand model would be a better choice since it supplies the location of each digit of the hand in the image. After doing research on what would be best for the Jetson Nano, we decided that using JetCam would be the best computer vision software for accessing images from the CSI camera. To perform image manipulation and operations, we decided to use OpenCV. OpenCV allows us to display, save, rotate, interpolate, and do much more to the images that we get from JetCam. This is very useful because we need to do a lot of image preparation to feed it into our models. Here's the software block diagram for our project. It describes the protocol for gathering images, putting them into the models, classifying them, and then performing actions based on the gesture that we see. Additionally, it shows the use of a buffer that prevents erratic behavior from the system if a gesture is detected for a single frame.
This block diagram describes the communication between the Jetson Nano and the Atmega 328P. Once the system is powered on, the Atmega will connect to the X and Y pins for the servo motors and establish a serial communication line with the Jetson with a baud rate of 9600. The Atmega will idle until it detects data on the serial buffer. At this point, it will read the first byte of the buffer. If it is a character X, it will capture the X and Y integer coordinates of the frame, which will be the center point for the window, for a window that the system will try to move to. The X and Y angle variables will step through the angles and write to the servo motor until they are within plus or minus 20 pixels of that center point. If the first byte is a W, then it will capture the W and H integers, which corresponds to the X and Y coordinates of the frame. It will use these values and the map function to map 0 to 180 degrees to a range of pixels we determine for the frame. Those map values correspond to the angles that the servos will move and will be written to the servos for actuation. If the first byte is an R, then the servo angles will be set to the center or 90 degrees to reset the system. The X and Y angle variables will then be updated to 90 degrees for future use. Once all of these are checked, the serial buffer is then flushed so that any additional commands it receives before actuation will be disregarded. Then the system will continue with its loop and wait for the next set of data on the serial buffer.
ImageCollection.py is one of 3 Python scripts that was developed for this project. It gathers images from the camera to be used in training the SVM model. It prompts the user for the number of gestures, the name of the dataset, and the name of each gesture to be labeled as. It also saves JSON files that assist the second script, svm.py, to actually train the model. It contains a GUI that you can see now for navigating dataset creation. It allows saving hundreds of training images in the click of one button, resulting in a very verbose dataset. The next script that was made was svm.py. It trains a support vector machine and saves it as a .sav file for use in the main program. It uses the datasets that was made in ImageCollection.py. It passes each image into the ResNet 18 hand model and gathers the location of the key points in each image, which is then passed into the SVM for training. It saves JSON files mapping the SVM outputs to the name of the gesture that was input in image collection. After the training is complete, a camera feed is loaded and allows the user to test out the gestures that they just trained. Articulate.py is the last Python script that was developed. It is responsible for the main logic in the behavior of the Articulite software. It issues commands to the ATmega328 microcontroller to actuate the motors in response to a gesture. When this script was in development, we noticed that sometimes the model would detect a single frame as a gesture and issue commands to the ATmega. This was an issue because it resulted in a lot of erratic behavior. To fix this, we made it so that gestures must be held for 1 second using a gesture buffer. It implements go here, follow me, and reset commands. Go here is activated by a thumbs up gesture. It sends a single command to the ATmega to actuate motors to center the tip of the thumb if it is outside of a center of frame. The follow me is a behavior that is activated and deactivated. It is activated by doing a rock on gesture, which looks like the horns on the hand. It continuously sends commands to the ATmega microcontroller to center the tip of the index finger if it is outside of the center of frame, until it is deactivated. Reset is activated by a peace sign gesture. It issues a single command to the ATmega microcontroller to reset the position of the servos to 90 degrees, which results in a neutral arm.
For our project, we thought about using a wall plug-in power supply or a battery pack power supply. In the tables below, you will see the difference between the two. For wall plug-in, it offers a 12-volt power supply and the cord length is 12 feet. However, for the actual length for our project from the wall, it was 8 feet. A wall plug-in offers stable voltage, allows for different length by using an extension cord, and it also has no discharge. For battery pack power supply, it allows for portability, stable and clean power, and you can use different types of batteries. These type of batteries include a 9-volt battery, a flat pack battery, or even a car battery.
During our assembly and testing of our circuit board, we realized we weren't getting a good signal between the ATmega microcontroller and the servo motors, which caused things not to function correctly. During the testing, we discovered it needed a decouple capacitor on both VCC pin 7 and 20 and A reference pin 21. During the retest process, we still didn't get a good signal and concluded the pull-up 10K resistor on the reset pin was the cause of the issue. Removing the 10K resistor from the circuit board fixed the issue with communication, and the PCB board was functioning as intended.
Next, we will be looking at the administrative part. Work distribution. As you can see in the table below, King and Michael focused on more of the hardware, such as the input power and voltage regulation, and Ben and Scott focused more on the software aspect of the programming and the gestures for the camera. Budget and financing. In the table below, you will see the parts that we use for our project, as well as the quantity of each part, the cost of each part, and the producer of where we bought the part from. Furthermore, at the end, the Articulite cost us a grand total of $450.07. Constraints. Some constraints that we had while designing our final project was the number of PWM channels that our ATmega 328 was able to support, which was only 6. We had no direct method to load code to the ATmega 328. We had a dimensional requirement of 10 by 10 by 10 inches to fit all the components into a case. We had to add a fan due to regulators and motors becoming hot during articulation. We had to make sure that the length of arm for the motors to handle torque requirements. And lastly, the FPS of our camera. Processing too many frames within 1 second caused lag, and gesture classification worsening system performance. Thank you for watching our presentation. We hope you all enjoyed, and thank you very much for being our professors and guiding us and educating us in our career field.